That's my contribution to an activity. Yes, Omar picked sleeping, the bed emoji. That's what I was going to go for, but I thought it would be too sarcastic. All right, excellent. Well, it is good to see you all. I hope you all have had a nice couple of days. Happy Thursday. We're getting close to Friday. Hopefully, you're feeling good about that. Plan for today is talk about algorithmic complexity. Just like Juan said, I'll go ahead and share my screen here. Right, cool. Cool. All right, so the past couple days we've talked about different searching algorithms, right? So we've written some code to search through arrays for specific items. We learned about linear search, where we're going through sequentially, right, one after another, searching for the item. Then we learned about binary search, where if we have a sorted collection, a sorted array, we're more quickly able to find the item we're looking for. Now, that distinction between those two is something we're going to talk about a bit today in terms of the algorithmic complexity. That is, how we measure these algorithms and determine that one is indeed faster, more efficient than the other. So that's the plan for today. So it's going to require a little bit of interaction and a lot of critical thinking, although not too much code. So just to preface that for you all. All right. If we have any extra time today, I'm not sure. This might take a little bit of time, or might take the entire lesson's time, rather. If we have extra time today, I can go over Project 10 if that's of interest. If it is of interest, please do share in our chat to let me know, or let me know that you're done with Project 10 and feel great about it. That would also be great to know as well. All right, so algorithmic complexity. In this lesson, we're going to learn about algorithmic complexity, including big O notation, which is one way we can denote algorithmic complexity. You're going to learn the different ways of measuring complexity and learn to measure the time complexity of an algorithm. So we're hoping that by the end of this lesson, you'll all be able to understand the basics of big O notation, analyze time complexity of some algorithms, and evaluate algorithms based on their complexity. That is the plan for today. You can see here our schedule is a few different chunks. We're going to begin by sort of talking about operations and doing some manual work here of measuring out some function calls. Then we'll get into big O notation and identifying the efficiency of some specific algorithms. All right, so a little recap. We talked about this before, but just a reminder, we're talking about algorithms. We're just talking about some sequence of instructions, right? So we've talked about it before as, this word maybe sounds a bit fancy and expensive in some ways, but really we're just talking about any, function that solves some kind of specific problem. For example, this function below is an algorithm. I want you all to take a moment to go ahead and read through this function and share out in the chat what is the purpose of this function. Right now it's called my function. Not very helpful, but if we were to describe this algorithm, how would we describe the purpose of this algorithm? All right, what do you all think? What is the purpose of this algorithm? All right, so Joseph says we're adding elements to an array. Yeah, for sure, right? We're adding some elements. Yeah, Juan is saying we're adding the same numbers multiplied at the end of the array. Sure, sure. All right, any other thoughts here? All right, so what we're looking at with this function, just walk through it real quickly. First of all, an important part of an algorithm is that we may have some kind of input, right? So this could be, for this algorithm, this is going to be our array. When we talked about, was it this week, last week? We discussed like finding directions, right? The inputs might be where you're currently at. If you were making spaghetti, like in that video, that might be the materials you have to make the meal you're trying to make. So we have an input here. Our algorithm then follows a series of steps to get towards some kind of outcome. So these series of steps are as follows. First of all, we set up a new array called result. We then loop over the length of our inputted array and access each element within that array. So that's what's happening right here, right? We're looping over all the items within the array and then accessing each element within that array. Then we're pushing into that new array the value we pulled plus itself. Once we're done with that, we've looped over the entire array and created a new array. We then return the result. So the output of this algorithm is that every element in the array has been doubled. And so we can see that here. So for example, if we inputted 1, 2, 3, we should expect to see 2, 4, 6. Any questions about that? All right. So this function has all of the markers of being a good algorithm. It has an input, it has an output, it has a specific goal in mind. There are precise steps, right? So pretty much anytime we're going to write a function, we're writing some kind of algorithm. And when we're analyzing an algorithm and trying to figure out how is this algorithm better than another? What's the efficiency of this algorithm? There's a lot of different things we could keep in mind, right? Probably one of the most important things when evaluating an algorithm is whether or not it's correct, right? If the output we get is correct, that's one of the first things we want to aim for, is to make sure our algorithm actually does do the thing it's intended to do, right? But once we have that, we might have two different functions, two different operations that achieve the same goal, maybe with the same inputs. And so we might want to be able to determine between these two different styles, is there one that is more efficient than another? So when we have to answer a question like that, like between these two different sets of operations, which of these algorithms is better than another? Typically, we will go and rely on two different types of measurements. So typically we want to think about the time the algorithm takes and how much space it takes up. So typically when we're measuring algorithms, we're thinking about time and space. So computer scientists typically measure complexity in terms of how long an algorithm takes to execute and how much space it occupies. But why does that matter? Well, in general, with the computers we have now, they're super powerful, capable of computing billions of simple operations per second. However, algorithms with particularly poor time or space complexity, time or space complexity is a way of saying our time measurement, our space measurement. Algorithms with poor performance in those areas may impact the user experience, the overall output in a noticeable way. And I'm sure you all have noticed this. I'm sure you all, in going to a website where the page couldn't load, or maybe you're trying to like click a button, but it's not being responsive because the page is overloading. I have a super old iPhone now, and so I feel like because of just the specs of my phone, every website is just asking too much of it. I'm always crashing and stuff like that. So it's pretty typical that you all have maybe experienced some algorithm not really being super cognizant of the available space or time that is available. You may also just have noticed this with I don't know. This is not really quite the best example, but I'm sure if you all have like downloaded a large file on like a weak network, it just takes forever, right? That time that it takes can affect your user experience as well. So as software developers, it's important that we consider these two measurements of time and space complexity, particularly depending on what the environment is we're working in and what kind of user experience we're trying to give. I'll add as well that for a lot of what we worked on in this course, and a lot of sort of the initial maybe like data sets or scopes of what you might be thinking of, you could write your code pretty badly and it would probably be fine. Because of how powerful our computers are, they can perform pretty well with pretty non-optimal solutions. So what we're thinking about here, for the most part, is we're thinking of huge data sets with thousands and thousands and thousands of records. You can imagine an array with 1 million elements inside of it. Or we're thinking of really complex processes that are having to do a lot of operations on a smaller data set. So we're still going to think about it, of course, with the smaller data sets in these examples. Just to give you all some context, like this is definitely super important to think about. It's also important to think about at certain times. I guess I want to help you all avoid stressing about every function you write and making sure it's the most optimal and performant. Really, the first thing to go for is to figure out how to get the function to work, right? Whenever you're writing a new algorithm, making sure you can get to the solution. And then a later step may be to optimize it, improve it, so that it's ready to account for, millions of different inputs potentially. All right, I think we're getting to an example now. Yeah, okay. All right. Before we get to that, just any questions on this? We talked about algorithms, we talked about how we measure efficiency, time, and space, and we talked about the importance of that. Any questions on those? Just says all good. I appreciate it. Excellent. All right, so one thing I guess, just as I'm moving on, I'll say when I talk about space too, I'm talking about like the memory space, like how much memory and space this is taking up in your machine. We honestly won't talk too much about space today. We're going to talk about time complexity more than anything else. All right, so let's talk about counting operations. So when discussing time complexity, you may imagine taking out a stopwatch to measure the amount of time an algorithm takes. And sometimes this can be an interesting or useful metric. For example, let's run the code here, and we'll see how long this takes. So I'm going to run it, and I'll talk through this code over here. So this code is running, but it's taking a moment to run. This function is called loop. It is given a certain length, and its entire job is to record a start time, record an end time, and between that, run a loop for a certain number of iterations. At the end, it'll give us some approximation of how long this function took to run. So I just ran it. What is this input? Good grief. What number are we looking at here? So we're looking at 100,000. It's 10 billion. Am I looking at that right? So that's a lot. That's a big number. For me, it said this operation took 11.744 seconds. I would love for you all to go ahead and run this code. You let me know how long this took for you on your machine. Dragosh is asking, is this based on machine power or internet speed? It's a good question. So I guess I don't exactly know how Codio works. I assume everything is delivered here in terms of the actual website and run on your own machine. So I'm going to guess it's on your machine as opposed to data going back and forth. That'd be my assumption. Joseph's already playing around with the numbers. Love it. All right, so initially, Joseph got 14. Sorry, I got 12. Timo got basically the exact same thing. Wow, we have the same setup, Timo. All right, so as we can see, there's a couple things that are interesting about this. One is that folks are getting some differences, right, in running the exact same algorithm. So that's not to say that, someone's computer is wrong, right, on how they're measuring it or anything like that. It's just that depending on the machine, depending on time of day, depending on how fast you click to run code, like there could be lots of variations. And if you actually run this multiple times, you'll find that there's actually variations between these numbers as well. So this is one of the reasons that actually timing out, like literally timing out algorithms, is not really the absolute best metric of what to do because there can be some variations. Omar, 21 seconds. Woof, computer's chugging along. right? So this is a little less precise, but it's giving us an idea of how long this takes. All right, now Joseph's on it is already messing around with this number here. So um, let's go ahead and adjust this number. I'm going to adjust this number and I'll do the same thing that Joseph did and bring it down from what looked like 10 billion to 1 billion. You all do the same and go ahead and run that and let me know what the time is you get now. So just going to remove one of those zeros and go ahead and rerun the code here. All right, I see that several people are typing. I love it. All right, excellent, y'all. That was much faster, right? That was significantly faster than our previous example. This is kind of interesting, right? When we reduce by a factor of 10 the number of iterations, um, it's going to significantly decrease. Dragos asks, what if instead of removing, we add one? I'll leave that to you. I don't know if I have all day to sit around here, but you're welcome to give it a shot. I'd be interested to know as well. Yeah, please do, please do. So this distinction, this difference between, okay, we did a billion versus 10 billion. That's a pretty big distinction. And that's kind of actually what we're trying to figure out in this lesson and in general, we're measuring the time complexity of algorithms is, well, is there some formula there? Is there some pattern that we can figure out for this algorithm as the inputs are increasing? How does that change the overall runtime of the function? So that's what we're going to be inspecting and doing some detective work today. All right, I'm gonna go ahead and move ahead. If you are playing around with the numbers, good on you. We have lots more examples and chances to try that as well. All right, so I'm gonna send it over to you all for a exercise. I'll take a few minutes, but let me go ahead and describe what it is we're gonna do. So we have the same function that we just had over here. We're gonna start to graph out how long each of these iterations takes and try and figure out if there's some sort of correlation between these things. So to do that, we're going to use the scatter plot maker. Let me go ahead and click on this. It's a perfectly fine website. So what this is going to do is it's going to allow us to make just a little scatter plot, a little graph. We're going to be able to track on one side what the size of the input is, and on the other side, how long it took. So I'll get started with you all here and do a couple examples, and I'm going to pass over to you to do all the rest. So for our graph, on our x-axis, that is the horizontal plane, we're going to represent the size of the input. So over here, I'm going to go ahead and just put it as a label, size of input. On the y-axis, that is the vertical axis, we're going to represent how long the program took. Length of program run, something like that. So those are our two graphs. I think I'm just going to try and put an example here just so we can see what we're going to end up with. Cool. So this is what we're going to end up with at the end, right? All right, excellent. So what I'm going to ask you all to do is we're going to copy this. We can copy this entire thing. And we can just paste this over here. You can expand these as well if that helps to kind of see what it is you're doing. So these are the values we're going to use, the number of iterations that are going to happen. And then we're going to measure how long the program took to run. And we're going to take kind of like a loose average and then input that into our graph. So to do that, what I would do is I would grab this first number. I'm going to paste it over here. I'll replace our value. What are we working with? This looks like a million. So this is a million iterations will happen here. And I'm going to go ahead and run the code. I would recommend, and it says so right here as well, go ahead and run your code a couple times. Often the values will be a little bit different. And then maybe pick the value that occurs the most, is the middlest value, whatever sort of makes the most amount of sense. Use your judgment here. So once I have this value, in this case, this took 0.003 seconds to run. That's pretty quick to run a million iterations. I'll take this value, I'm going to head over here, and I'll paste that in our y values. So what this is showing is that at the 10,000, or sorry, 1 million iteration mark, it's taking 0.003 seconds. And oh, well, I guess I can't graph it until everything's full, but once we graph it, we'll see those points show up. All right, so that is the plan for the rest of these iterations. So I want you all to take a few minutes and go through this and go ahead and paste over these values. Keep track of how long each program took, and you're going to paste those values over here into your scatter plot maker to make that graph. Once you're done, go ahead and take a screenshot of your graph and let's paste it to the chat and see if we can figure out what the trend is, if there is any kind of trend or what it looks like for everyone. All right, let me pause there. Any questions from you all on what we're doing? Any questions on what we're doing? Does everyone have their marching orders? Everyone understands the task at hand? Track, let's just chill, man. Just slow down. All right, much appreciated. All right, cool. Sounds like some folks are already working on it. Let me pass over to you all. I'll stop sharing here and give you all a few minutes to do this. Once you have a graph, go ahead and share it. Thank you, thank you. All right. So there's a little of a trend here in some ways. I mean, we can see that the numbers get bigger, right? We're heading sort of up towards the top right corner of the graph. We can also notice there's a pretty good amount of variation between all of these, even if there's sort of a general trend line. So a couple things about this, and then we'll move on to the next one before we really debrief this activity. But this is again why I think counting the seconds is not always the most useful way to measure algorithms. Why we end up using a more abstract version of it is because there is going to be variation depending on the computer, time of day. A lot of different things could change sort of why we end up with certain times or not. And as we can see, there is a general trend here as well. So there's probably some relationship between the code that's getting run and the size of the input and what the operations are inside of here. Oh, thank you. Well, yeah, let me go ahead and share my screen. All right, cool. All right, so let's get back to it. So we saw some good variations there. Let's go ahead and do this one more time. This time we're going to do it with a different type of algorithm. And we're going to see if that changes the types of graphs that we get. Awesome. Thanks, sorry. Looking good. Yeah, it's a nice graph. So we're going to do this one more time so you can refresh this page to restart. We're still going to do size of input. Oh gosh, if I can spell it. Yikes. And number of iterations. I'll put here in seconds. Can expand these a little bit. So this function, so you all can go ahead and get started if you want. If you're just ready to go, we're going to do the exact same thing here of changing our input value here and mapping those, but just talk through the function a little bit. This function is going to, when given some kind of array, it's going to loop through the array, and it's going to multiply all numbers by each other. So what we can see here is it's taking an array. If it's not an array or if there's no elements in there, it'll just return immediately. It's then recording the current time, and then it's looping through the array and grabbing I, and it's looping through again and grabbing J. So we have a nested for loop here. And we're grabbing those elements and multiplying them times each other. So no real output here. This is, again, sort of a dummy case to sort of try something out. But this algorithm is a little bit different than the one we saw previously. Then we grab that end time and get our measurement of time. All right, so that is the plan. This is a little interesting algorithm code snippet, I should say, down here creates an array of a certain size. So at this point, we're actually changing the size of an array as opposed to just the number of iterations. So actually, I guess I should say over here, size of array, and gosh, I messed this up, didn't I? X is going to be the size of the array. Okay, size of array. I had that correct the first time. Time taken. Okay, let's do that. So I will pass over to you all again. Again, how you're going to do this, you're going to take one of these values. We're going to plug this in. Go ahead and run our code, run it a couple times, just kind of see what we get. I'm seeing here 7.1, 7.1, 7, 7.2. And then over on this side, we'll go ahead and make sure we record that correctly. All right, I'll give you all a few minutes. I'm gonna stop sharing, pause recording again. And once you have that done, go ahead and share your graph in our chat. Thank you. All right, so what I want you all to take a moment and do is take a look at the graphs you created, at the graphs that your fellows created, and let's just discuss some of the differences between these two graphs and these two algorithms. So what are some of the things that you notice? What are some of the things that you noticed while running it? What are some things you noticed in looking at these images? What are some of the differences here? What do you all think? There are a number of differences just between these two different graphs and these two different algorithms. What are some of the things that you're noticing? This is our detective work part of our lesson. I'm going to figure out what is different between these things. Thinking hard. I'll give you some encouragement. Let's see, hi, bud. Oh, here we go. Yes, he has a little sweater on. He's just so excited you're running algorithms. All right, what are some of the differences that you all noticed? What are some of the differences?
Dogs are wonderful.
Yeah, he's a good guy. He's just constantly sleepy. Nothing. They're the same. There we go. We got that several people are typing. I'm not looking for a right answer here. I'm just looking at what you all notice. All right, thanks. Sorry, points out it took longer for the second algorithm to run than the first. Yeah, so even just the times we took, right? Excluding everything else, the times increased in the second algorithm. Excellent. What else? All right, Omar shares second one is pretty linear. First, second one's very linear. First one looks like a curve. Increase the x, the times gets bigger faster. Right, so there's some relationship in terms of the shape that these things are putting together, for sure. Yeah, there's some shape to the graph. What else? What else did y'all notice as some differences between these two? Joseph, I like this. Okay, so there's more differences in time in the first graph after 500,000, but the second is more uniform. I think that's a good point. Yeah, so looking at the first graphs from us, we all kind of they're all kind of going wild. The first, there's a couple of deviations for everyone there, right? Um, whereas maybe the values are a bit more consistent in the second option. Yeah, I like that. Anything else you'll notice? How about the algorithm itself, the difference between the two algorithms? And I'll share my screen here. We can kind of flip back and forth. Let's head over to our first one here. So this is our first algorithm. I'll copy this over and just compare it here. So this is our first one. Oops. Any differences of what you all notice between these two algorithms? Anything stand out to you? Any differences you notice between these two algorithms? Sure, Omar says the amount of code. Yeah, right. One just has more code. Like you're saying that like, oh, I don't know, but like that's a really good point, right? There's more code in what perhaps that affects the runtime. What else do you all notice? Some stuff's the same, right? We're measuring start and end time, doing that in both. We're doing some kind of check here to sort of return early. Our return statement is the same. So I think there's a couple of differences you could point out here. One is the type of data that's getting inputted, right? In this first option, we're inputting an integer, whereas in the second algorithm, we're inputting an array. So maybe that has some effect on what's going on. In this first one, we're just iterating. In the second one, we're doing multiplication. Perhaps multiplication has an effect on what we're doing. In this first one, we have one for loop. In the second one, we have two for loops. Perhaps that has something to do with the overall runtime, why it's taking a bit longer. So we'll talk about what is most impactful of these algorithms. This sort of detective work, I really appreciate you all doing this with me. This is the kind of stuff we want to be able to look for within an algorithm, is trying to identify, figure out, okay, why might this be running slower? What are some of the differences here? What can we identify as some of the ways in which these algorithms differ, right, in terms of their overall output and their overall implementation? All right, excellent, y'all. Let's move ahead. So here's what hopefully our graphs ended up doing. I think realistically, I don't know. To me, they all kind of look the same, the graphs. But here's where we might have ended up, or particularly if we kept adding additional numbers, or where what the hope was. So in the most recent exercise, the second algorithm, we may have noticed there's a bit more of a curve at the very end of the graph. I think Asari's kind of has this. Omar's kind of has this. Um, Joseph's kind of has this as well. I think mine, Tima's to a certain extent, maybe looks more just linear. And again, this is because there's a lot of so nothing that any of us did. It's more just trying to measure these out in terms of literally seconds is going to have a high amount of variability. When we look at the first one, as we talked about, there's a lot of variation here. Um, but ultimately, we should be able to draw a more linear path through the first example. So computer scientists have noticed that certain algorithms follow some kind of particular curve if they are to be measured based on the efficiency of an algorithm. And those curves can share some information with us about how efficient these programs are. And the efficiency is really determinant on the input coming in and the number of operations getting run. So instead of providing a number of seconds for algorithm, or trying to do this kind of graphing and average a bunch of values, right? Running a function at the specific, number of inputs a million times and taking the average. Instead, they've developed something called big O notation. So let me give you the definition here, and then we're going to define these terms. So big O notation is a mathematical notation used to describe the upper bound of an algorithm's running time or space requirement in the worst case scenario. It provides a high-level understanding of the algorithm's efficiency by focusing on its main contributing factors, ignoring lower-order terms and constant factors. So in the next few slides, we're going to talk about what each of these bolded sections mean. But just to linger here for a second, the idea here is that we're building an abstraction to talk about these kinds of graphs. All right, that is the goal here. So big O notation represents the German word. Someone fill in here how to say this. Ordnung, perhaps, meaning the order of approximation. Measuring algorithms in terms of their big O means to provide a generic representation of how long an algorithm would take as their input size grows. So we're not going to be referring to seconds or milliseconds or anything like that. We're not really using a unit of time in that sense. We're using an algorithm a representation of how long it will take as the inputs increase. So as you've seen, algorithms can be measured and may take a predictable amount of time as the size increases. Big O is represented as a mathematical function that would generate a particular shape on a graph. For example, the first exercise would be considered to have a big O of n. That might look like you typing out O of n, where n represents the size of the input. An O of n algorithm can also be described as linear. That is, the input size increases the number of operations performed, and those operations performed increase at a steady rate. So we can see this is our big O complexity chart. You probably see this plenty if you do any prep for interviews. The O of n representation, the linear representation, is this line right here. Before we move ahead, let me just be really clear on what this is showing. So this is on the y-axis, the number of operations that occur. And on the x-axis, the number of elements that are being inputted into whatever this algorithm is. What this is saying is as the number of elements increases, the number of operations to complete that algorithm increases at a linear rate. Very generally, you could say if 3 inputs were added into it, it takes 3 somethings, 3 units of time, right? It just constantly goes up in a straight line. It's predictable in that sense. Let me pause here for a second. Any questions on that, on what this graph is saying? Feel somewhat sensible. It says here elements, right? And that's saying the number of elements. That could be the number of like arguments in a function. Most often when we're talking about this, we're talking about like the number of elements in an array or in some kind of collection. So the difference between an array with 10 items versus 10 million items, that's typically what you're going to hear. But more generically, it's just the number of things coming in, the number of elements coming in. For operations, the number of operations that have to be completed to actually finish the algorithm, to get to the very end of it. This could be measured with seconds. Like often the more operations, the more time it will take. That is what we're saying here, but we're not putting a specific number on it. We're not saying for each operation it's taking 0.001 second, right? So we're abstracting it a little bit. All right, cool. There's silence, which means either going really good or really bad. I think either way will move ahead. If you have questions, let me know. This is pretty important to understand. It's only going to add in complexity on this. So please do feel free to ask. Happy to talk more about it. All right, so we talked so far about big O notation, mathematical notation. I guess I'll just add to in terms of mathematical notation. We don't really need to know any math. If seeing the word math makes you break out into cold sweats or anything like that, don't stress. There's no need. We're not really doing any math, just a different type of notation. So let's talk about the part of that definition was talking about the worst case scenario. So when measuring algorithms with big O, you should only be considered about the worst case scenario. This means you should assume the algorithm will take the longest amount of time or most amount of operations possible. Why is this? Well, software developers are just pessimistic. There's just no hope. We just think, well, it's going to take as long as it could possibly take. That might be one reason, but we also just want to make sure we're accounting for all situations, right? So we want to account for, hey, in the worst case scenario, everything's gone wrong. How bad could this get, right? That's the boundary at which we're going to really do the most amount of definition. What's the worst case scenario? For example, let's take a look at this function, which is going to randomly guess numbers between 1 and 100. So let's take a look at the function. So we have our function that's called guess number. It takes in a target value. So for example, here the target value is 11. It defines two new variables, guess and guess count. And while guess does not equal target, it's going to reassign guess and go ahead and just pick a random number between 1 and 100. And then it'll increase the guess count. So this is going to keep guessing until it gets that random number. So let me run it a couple times. You all also run it a couple times. So you can see here, the values I'm getting are pretty wildly different. So searching for 11, in one case I made 200 guesses, in one case I made 27 guesses, in another case I made 193 guesses. All right, you all take a moment, try this out. Tell me what the highest number of guesses is you got and what's the lowest number of guesses is you got. No work here, just run the code, see if you can notice any big swings. Well, mine are pretty consistent. Oh, there we go. Lowest and highest, what do y'all got? 2? Nice, nice, I think I was trying this earlier this morning just to like run through it, and I got the first guess. It grabbed it. I was flabbergasted. 15 and 4 or 5. Whew. Nice, nice. Yeah, I got 587 here. 6 and 277. Cool. Cool, cool. I just said I got 4 now. All right, nice. Yeah, so theoretically, in the worst case scenario, this could just always run, right? This function could never stop. Perhaps the computer just constantly picks random numbers that are never the target number. It's unlikely. As we're seeing, usually it stops, but the number of guesses can wildly vary, right? So we would say this is a pretty inefficient function. And if we wanted to make this more efficient, maybe we would do something like putting together a list of the numbers we had already guessed, right? To make sure that we can't ever make more than 100 guesses. But as it is right now, the computer could just say, hey, is number 99? How about 99? Is 99? How about 99? And you could just do that forever. So we want to account for, we want to think about the worst case scenario for our algorithms. All right. I don't know why. I just find this endlessly entertaining. I just feel like it's fascinating to see how many it figures out. Excuse me. All right. The last little bit of the definition there was that we're going to ignore the small stuff. So let's consider the big O of the program to the right. I think this is the file from earlier, so I'm going to delete this part. I think it's just talking about this. This function takes the first number in an array and then multiplies it by itself and every other number in the array, then repeats the process again with the next number. Consider the amount of operations it needs to do as the array size grows. So as the input is just an array of just the number 1, right? Then all it's doing is 1 times 1. If its input is 1 and 2, it does 1 times 1, 1 times 2, 2 times 1, 2 times 2. If it's an array of 3 elements, do you notice how quickly this is going up? Right, it's doing 1 times 1, 1 times 2, 1 times 3, 2 times 1, 2, 3, 3 times 1, 2, 3. So if the array is length 2, 4 operations occur. If it is 3, 9 operations must occur. This kind of function is called quadratic, or it has a big notation of O of n squared. Just to head back over here real quick, is this one? Oh, where's that cool graph? Right here, cool. So you can see O of n squared is over here. This chart describes it as horrible. Seems a little intense, a little rude maybe, but because this is quite different than O of n, right? And this kind of, I know our graphs kind of looked a little all over the place at times, but in terms of how long things took, this does actually seem kind of right, right? Our O of n squared algorithm certainly took much longer than our O of n algorithm. So the idea is that as the input size increases, the overall number of operations needed to run increases. And in the case of this algorithm, it's increasing exponentially, right? So whatever that input size is, we're multiplying it by itself to understand the number of operations taking place. Now, in this, you could nitpick this measurement and point out that there's technically more than O of n squared operations. For example, storing the time here, this is an operation. This is an operation. Returning, that's an operation too. When we're talking about the number of operations, really every line of code, every time the computer has to do something, perform some task, that is technically an operation. However, we're not really concerned with these sort of small potatoes kind of operations. We're concerned with the overall trend line. When we're talking about big O notation, we're just focused on the overall trend line. So we'll see some examples of this, but the goal is not to, with the fine-tooth comb, go through your algorithm and be like, oh, here I'm assigning a new variable, so that's going to increase the time. If in an insanely slow system, perhaps that would make a big difference, or in like a very small little, I don't know, Internet of Things kind of tool, perhaps those kind of operations can matter. There are actually some really interesting videos about this. If you all are old enough, I'm getting very old. If you all are old enough for like to play it or know about like the NES or SNES or some of the first like video game consoles, they do a lot of really interesting stuff to fit everything within this very small amount of computer space that was available to them. Now we're not as concerned about variable assignment or something like that. We're really concerned about the overall trend line and what that means for the overall number of operations happening. And again, how the input affects the overall time complexity of our algorithms. All right, let's continue on this in terms of ignoring the small stuff. So again, our goal is to figure out what the trend line is overall with our algorithms. So in this more complex function below, we can actually see a couple different measurements that could happen in here. So this one, this function is called multiply all elements. It takes in an array. We can see here it does some kind of check to see, hey, is the array empty or is it not an array? Go ahead and do something. It then logs out all the values, and then it goes through each of the values and multiplies them by each other, just like we saw with that previous algorithm. So this step right here, we would describe as O of n. The reason we would describe it as that is because as the array size increases, the number of operations is going to increase as well. So if we have an array of 5 items, this console log statement will run 5 times. If it is 5 million, it will run 5 million times. Down here, this chunk of code loops over the array and loops over the array again, and is going to be a quadratic formula. It's going to run, our big O would be O of n squared. That's because, as we saw in that previous example, is this one with the table? Yeah. It's following this pattern, right? So if we have an array of 2 items, it's going to run 4 times. If we have an array of 3 items, it's going to run 9 times. So we could represent this algorithm if we wanted to be really precise. We could say, okay, well, maybe ignoring, particular statements like this or the console log. Even if we ignored that, we could say, okay, this has a big O notation of n plus n squared, right? Because you're saying this part of the equation is n, and this part of the equation is n squared. So that is true. That is a good measurement. However, in terms of what we would actually, how we could just talk about this, how we'd really talk about it in an interview or with our coworkers, is that we'd actually reduce even this kind of equation to just its largest components, the worst components, right? The things that take the absolute longest. So in this case, we actually reduce this equation to account only for its largest measurement. This means that big O of the algorithm would be O of n squared. That's how we would talk about this algorithm. So that's O of n squared, the worst case scenario. And so again, going back to our little chart here, in an algorithm, even if there are some aspects of the algorithm that have like some better measurement components down here, all we're concerned about with the algorithm is what is the worst thing? What's the worst possible situation? So we can think of that as if at any point in the algorithm we measure some sort of section of it, which is higher up in this list, which takes longer, that's the measurement we stick with. Because over time, as the amount of inputs increases an insane amount to 5 million, 10 million, 10 billion, that's the shape of the graph that takes precedence. That's the overall shape that's going to matter much more in, again, the worst case scenario. So we'll talk about how to better identify these efficiencies in just a moment, but when we're identifying them, it means we basically want to look for what's the crunchiest part of this, what's the most difficult, time-intensive part of the algorithm to figure out what the measurement is. And if we're looking at them sort of on the page, it means we can also reduce them down to the highest value. So for example, if we wanted to measure an algorithm, let's say we saw an algorithm measured as O of 2n, that is just O of n, right? Ultimately, that multiplication matter doesn't really matter at the end of the day. O of n squared plus 10 would become O of n squared. O of n plus 9,999,999 becomes O of n. O of n squared plus 999n becomes O of n squared. We're just taking the worst value. So in some ways, this part of it does actually make our job trying to evaluate algorithms a little bit easier, and that we're just trying to pick out what, again, the crunchiest, the worst bit of the algorithm is, and that's how we're measuring it. We could do more fine tuning, but that's the thing we're most concerned about. All right, let me pause there. How's everyone feeling? This is like heady, thinky, computer sciencey kind of stuff. Any questions you all have? Any feelings you'd like to get off your chest? Comments, complaints, compliments, criticisms, uh, gifts, emojis, thoughts and prayers. What do y'all think? At the moment, we haven't actually talked about how to identify this. We've just been talking sort of high level about the different measurements. Yeah, Joseph says, just interested. I love that, Joseph. I'm glad. I think it's pretty interesting too. And yes, this does come up during software engineering interviews often. I guess I'll say from my experience, you may be asked to put together an algorithm. Often you'll talk about it first, then you would implement it, and then you maybe talk about how efficient it is, where it can become more efficient, something like that. And being able to talk about the big O is really valuable. It adds a lot of credibility to your ability to talk about code. And it also means you're able to identify where some things are bigger problems than not. Whereas GIF and words are at odds with each other, but I'm glad it seems good for now. Great. All right, excellent, y'all. Well, it's definitely a lot of information, a lot of heady stuff. So far, we haven't gotten into how to measure these or sort of actually measuring some algorithms. I've sort of just been telling you the answers here. Hopefully that's felt helpful as we've been able to play around with this. We're gonna go ahead and take our break. So we'll take a 10-minute break here. Once we come back, we're then going to take a look at how we can measure these algorithms best. And we'll do some work in our lab of actually measuring out some algorithms and figuring out what some functions do. So let's take our 10-minute break. See you all back about 25 minutes after.
Hello, everyone. You can drop a thumbs up in live chat if you're here.
All right, looks like Joseph's here with us. Anyone else here with us? You know, back?
Okay.
And we're still alive. Hey, that's great. It's good to hear.
So you almost survived to the metro today.
All right. Sorry, sliding back in. All right, cool. Shall we continue? Anything you wanted to add, Juan?
No? Go ahead.
All right, excellent. I'll share my screen here.
We can see it now.
All right, perfect. Okay, hope you all had a nice break. Did y'all do anything interesting? I just unsubscribed from a bunch of emails. That was really, it's really not exciting, but it feels good. It feels good every time I hit that unsubscribe button. Pro tip, if you want to not look at all the trash emails you get, you can just set a filter. If it has the word unsubscribe, it just goes to archive. I think that's the thing to do. My partner does send me, try and forwards me things, and I never see them. So that, I guess that is a negative, but sometimes you just gotta do what you gotta do. All right, well, hopefully you did something more fun than what I did. We're gonna do the rest of the lesson today. First of all, we're going to talk about what we're looking for to measure algorithms. And then we'll have a little bit of time to work with the lab where we're going to ask you all to identify what some functions are doing and what you believe the big O notation of those functions is. All right, so first let's figure out how we can measure some of the algorithms we'll be working with. So in general, to effectively measure algorithms, we're pretty much always going to be looking for the number of iterations that occur in an algorithm. What we mean by that is, as we saw with those graphs, the number of elements coming in will increase the number of operations. It's rarely the case. I feel like you'd have to set up sort of a weird scenario where you have tons and tons of inputs, and you're iterating through all those inputs, but you're not using any kind of looping mechanism. Typically, you're doing something with like a for loop or a while loop. And so typically when we're trying to measure the efficiency of an algorithm, we're looking for those for, while loops, any kind of iteration style of code. That also, though, means we're going to account for any kind of native array method, which also would iterate. So that means things like for each or map or filter. It also means things that you may not think of when you think of iterating through. So for example, there's two functions down here. This one is called getIndex of manual, and this one's called getIndex of native. So in this first function, getIndex of manual, this is manually finding the index of an array. And so we can see here we have array, we have the element we're looking for. We'll search through the array using linear search. As soon as we find it, we then set the result equal to that index, and we end up returning the index. Otherwise, we just return -1, right? So this is our linear search algorithm that we talked about a few days ago. The getIndex of native function just uses the index of native array method in JavaScript. So you may look at this and go, oh, nice, right? This one has a loop, and then this one doesn't have a loop anymore. There's no for loop. This one has better efficiency, right? And that is not true. So index of has code happening underneath it, right? There's code underneath index of, which is going to be looping through the array. The index of method is not doing anything magical. It's just running additional code using this nicely named method to make it easier for us, right? So as developers, it's nice to have index of because it's a quick, way for us to type it out, but there's still an iteration happening under the hood. In general, it's going to be, it's not necessarily possible to know the implementation of every single native array method. That's not what we're asking of you. But you do want to think about when you're using a native array method like index of, or what else, dot includes, or like dot filter. Just kind of think through, what is this doing? What do I think it's doing? Do I think it's iterating over this set, this collection of data? And if so, you want to account for that as, even though it doesn't say for or while loop, that is probably some kind of iteration. So again, our goal here is we're looking at functions to really try and identify where there are some iterations happening, where there's some looping happening. And based on that, figure out what the big O notation is. There's a link here that brings you to a website that shows the underlying implementation of index of in some kind of pseudocode language. It's kind of interesting, but I'll leave that to you all to explore. All right, so here's another graph showcasing some different shapes of our big O notation typical measurements. We have linear, quadratic, logarithmic, constant. So we'll talk about these four different measurements and what this could look like. So for constant algorithms, a constant algorithm is one which we call a constant as constant time complexity. This means that it generally takes the same amount of time no matter what the input is. So simple functions that do not rely on iterations will often have a constant time complexity, even if there are many lines of code. So just because there's lots of lines of code doesn't necessarily mean it's going to take a long time. We have an example down here of get theme. So it takes some key and determines whether it's light mode or dark mode. There are no iterations in this code. It's just checking some values and returning something. No matter if the key here was, I don't know, super long name or something like that, it would basically take the same amount of time. Now that amount of time may take a while. So for example, perhaps we had a get theme function that for whatever reason, we said, hey, go ahead and wait for 1 second before you return the result. That's still going to be a constant function, even if we built in things that might take time, because the input does not change the overall efficiency, right? The input doesn't really matter there. It's just going to take the same amount of time. It's constant at the end of the day. Constant functions are going to be rare in terms of doing anything really interesting. They're often going to be pretty simple functions, but are also you'll end up writing lots and lots and lots of constant functions because these are kind of like helper methods. Something linear with a linear time complexity often means that does mean as the input increases in size, the number of operations increases linearly. Simple functions that rely on loops can often be linear if they do not rely on nested looping or nested data structures. So many accumulation algorithms are O of n or linear. So here's an example here of find product by ID. We can imagine a list of products, perhaps an array of objects and a specific ID. We then loop over the array, grab each product, and check to see whether or not the ID is there. If it is, we'll go ahead and return that product. Otherwise, we'll return null. So the reason this is O of n is because the worst case scenario is that we have to go through every single element in the products array. Worst case scenario here is that we're looking for a product with an ID that does not exist or doesn't match, right? So if the number of products is 1,000, the worst case scenario is that we may have to go through 1,000 elements before determining that it's not in our list. Best case scenario is that it's the first one, right? But we're not concerned about that. We're just concerned about the worst case scenario. So as the input size increases, so does the number of operations within this function. For quadratic time complexity, a quadratic function, this is O of n squared. This means that as an input increases in size, the number of operations increases quadratically. So we saw this earlier. If the input size increases from 2 to 3, the number of operations may increase from 4 to 9, right? So it's not just a matter of 2, 2, 3, 3, 4, 4, right? Where with a linear, we would expect it to be linear in that sense. With quadratic, it's saying as the input increases, it's really going to crank up the number of operations. Functions that require multiple nested loops are often referred to as quadratic, particularly when both loops must iterate over the same or different arrays. So we have an example here of finding matching hobbies. So we can imagine that we have Alice, she has an array of hobbies, and Zane has an array of hobbies as well. And what we're trying to do here is provide a list that includes just their matching hobbies, the ones that are exactly the same. So this is O of n squared because, oh, we have a really nice little example down here. As the array size increases, the number of operations is going to increase as well, right? We're having to do multiple checks on both of these arrays. Unless there is a limit to the size of the arrays or as to how many times the array is checked, the number of operations can increase quite quickly. So this also just to point out here, these could increase the same size. So we could say Alice has 10 hobbies and Zane has 10 hobbies. That's still going to be O of n squared. Or it could be unequal. Perhaps Alice has listed 3 hobbies and Zane has listed 100 hobbies. Either way, we're saying worst case scenario in this function, worst case scenario, they both listed 10 million plus hobbies, right? Both of these arrays are as huge as possible. And because of that, we have to account for both of them and assume they're going to be as long as possible. So we're saying O of n squared. And again, the signifier here, the thing to look for is this nested for loop. As soon as you have a nested for loop, you're probably looking at, not always, but probably looking at an O of n squared algorithm, particularly if those for loops or those while loops are iterating over the entire length of the array. All right, this last one, we're going to talk about O of log n. So an algorithm with a big O of log n is referred to as having a logarithmic time complexity. This means that as the input increases in size, the rate at which the number of operations increases will slow down significantly. So we've looked at this graph. I haven't talked about it too much. So we see linear here, we see constant, we see quadratic. These are kind of what we'd expect, right? As n increases, as the input size increases, more time is getting taken or the same amount of time is getting taken. Logarithmic is really interesting because what it is saying is that as n increases, it actually gets better over time, right? The curve tapers off. So there's a certain point where we're not really seeing a huge increase in the amount of time it's taking. Now, I know saying logarithmic can add that cold math sweat to you. No worries, we don't really have to understand logarithmic functions super deeply to understand logarithmic complexity. Logarithmic functions and algorithms typically include some kind of loop. At some point in the loop, the algorithm makes a choice between multiple paths. And at that decision point, only one choice is made and all others are excluded. Does it sound familiar? What did we talk about recently? Right, like binary search is an excellent example of a logarithmic function. Unlike linear search, which examines each element sequentially from front to back, binary search divides the search space in half with each step, which drastically reduces the number of operations as the array size increases, making it much faster. So before, in the past few lessons, we had a sense, right? We talked about why we felt like binary search was overall better because it was able to more quickly find a solution. Now we have a way to talk about it. Linear search is going to be O of n, whereas binary search is going to be O of log n. And looking at this graph, we can see that at a certain point, right, we can see the linear line here, we can see logarithmic. They're may not be much of a difference at perhaps certain points in the time complexity, right? Perhaps at a certain size, like linear can work just as fine, if not better. But thinking of, again, the worst case scenario, logarithmic function will always do better in the long run. All right, let me pause there. Any questions on any of these or in identifying how we can identify what time complexity a function has? So again, with constant, we're looking for essentially no iterations. With linear, we're looking for probably just one iteration. With quadratic, we're probably looking for a nested set of iterations, so a loop in a loop. And with log n, we're often looking for some sort of decision point breaking where we're cutting off half of the input somehow. Okay, all right. Well, I think you all are pros now. Let's give it a shot. So we're gonna head over to the lab. I'll give you all a bit of time to work on this. This is definitely gonna be, I hope, interesting and a challenge. Here's the good news: you don't have to really code anything. You just got to read some code. Easy, right? Just take a look through. No problem. No need to figure out or look up anything. Just trying to figure out what this code does. So the task is here. So we have a number of functions here. I believe there's 7. Yes, there are 7 functions here. For each function, I want you to write in the comments up here 2 things. First is a description of what the purpose of this function is. So just describe what this algorithm is doing. Then I want you to identify what the time complexity is. So again, you want to think of the input, what the input is, and how that input influences the overall, how many times it influences the operations in the function, in the algorithm, and whether that is a linear relationship, whether it's quadratic relationship, something else, et cetera, et cetera. All right. You don't need to run the code here to figure this out, but you can, if you want, you can run the code and you can see there's some nice output here. This could help you maybe figure out sort of what the output is, what the purpose is of these functions. Any questions before I send you off on your own? Everyone's feeling great? Everyone's feeling like, I got this. Easy. Totally easy. All right. We'll see. We'll see how it goes. Give your best shot. If you'll have questions, please do ask them in the live chat. We'll give you all at least 10 minutes here. I think this will probably take a little bit of time to figure out what all these functions do, try and measure stuff. If you get to a good spot though, please do just give a thumbs up in live chat or something to let us know that you're done. And of course, again, if you're stuck, let us know that too, so we can try and help unstuck you. All right, I'll stop sharing my screen, pause here, and give you all a bit of time to work on this. Good luck. Folks stuck on a certain number, still halfway through. Sure, yeah, still working on it. All good. Okay, yeah, all good. Let's do this. We'll take another, make sure to have time to go through some of these. Take like 8 minutes more. Let's say that. At that point, just get as far as you can. If you have questions on stuff, you're feeling stuck on one, maybe just add a note on what's confusing you and then move on to the next. And then we'll come back together and we'll walk through all of these, talk about what the functions do, and talk about the time complexity of all of them. All right, I'll pass it back to you all. So let's take another 8 minutes or so. Again, if you have any questions, please do ask in live chat. Thanks. All right, thank you. All right, hopefully that went okay. At the very least, interesting. Let's go ahead and walk through some of these together. We'll talk about some of the ways to measure these and what the functions do. Let's start with the first one here. This function is called stringify. How would you all describe this function? What was the purpose of this function? But you can just copy and paste or share in the chat. How did you describe this function? And I guess I'll run the code over here too. What do y'all think? What is the goal of this function? Excellent. Thank you, Omar. This converts the values within the array to a bunch of strings. Pretty straightforward. So we can see here the input is 1, 2, 3, and what we get out is 1, 2, 3, all of them as strings. Excellent. All right, so that is the purpose for a stringify function. What did you all put down for the time complexity of this function? What do you see as the time complexity here? All right, excellent. Joseph's writing in O of n. Linear? Yeah, exactly, y'all. All right, so let's talk about how we know that. Right, so how we know that is taking a look at this array. This is our input, right? As the input size increases, as the length of the array increases, we're going to do more and more and more iterations. So because of that, as the input increases, the amount of operations are going to increase linearly compared to that, which means we end up with O of n as our big O notation for this function. Excellent. So reminder, these other operations, they're all operations. They all count as part of, I guess if you had a million lines in between here, it might take a little bit longer. But the most important thing that's happening is this for loop. All right, excellent. Let's move on to the second one here. This function is called pluck. What is the purpose of the pluck function? What's the purpose of this function? Yeah, excellent. Thanks, Omar. So we're randomly selecting one element in the array. Randomly selecting one element in the array. So we first grab a random index based on the array's length, and then just return that number. So you can see here in this case, it returned the value 1, but it could have returned 2 or 3. All right, what is the big O complexity of this function? What did you put down as the big O complexity? This one's a little bit trickier. All right, we got some question marks. Yeah, just guess. Who knows, right? Yeah, so it just says O of 1. Omar says constant. Yeah, exactly right. So this is a constant algorithm. You may look at this and say, okay, well, as the array increases, the length is going to be larger, right? So maybe that affects it, but we're not increasing the number of operations. We're not increasing the number of iterations as part of the array increase. It's just changing the multiplication. That's not really going to affect the overall operation. So in this case, we're looking at O of 1 or a constant algorithm because we're just performing some calculations and returning a value. Also important to note that accessing an element within an array is just an O of 1 operation itself. So it doesn't require any iteration or searching or anything like that. All right, excellent, y'all. How about this next function called chunk? What is this chunk function doing? What does the chunk function do? I feel like this is hard to just read and guess, but the output over here might share some clues. Excellent. Thanks, Timo. So Timo says dividing the array into smaller chunks. Yeah. Smaller chunks determined by one of the arguments here, right? So we see the inputs here are array and size. And so down here, right now, the value of size is 4. We can see what we get back as an array of arrays. The first array has 4 elements, second array has 3 elements. Let's go ahead and try and change this to having the size be 2. You can see now it tries to chunk the array into little groups of 2 with the remainders left over here. All right, so that's the purpose of our function. What is the time complexity of this function? What is the time complexity? Do you think it's constant, linear, quadratic, or logarithmic? I guess this is kind of like a multiple choice. Okay, just guess your way through this. All right, Omar shares O of n. Folks agree, folks disagree. All right, sounds like folks agree. Yeah, I would agree here. I think this is O of n, a linear algorithm. So we can see that, right? Because as the array length, as the array size increases, we're going to be doing more and more iterations to make more chunks of data. All the content in here, interesting and essential to getting the function to work. It is not going to affect the overall time complexity compared to the fact that as the array size increases, we're going to end up with more and more operations running. All right, excellent, y'all. For these next 4, all the functions are going to use this data below. So we have this array of objects. These objects have 3 keys: ID, name, and paid. ID is an integer, name is a string, and paid is a Boolean value. Seems like it's representing guests to party or an event or something like that. All right, so search by name. First of all, what is the purpose of the search by name function? It's a tough one. It's real difficult, I know. What is the purpose of the search by name function? Or says search a name. It's true. It is going to search a name. What are we getting back from this? Maybe that helps to describe it a little bit further as well. And we can see over here. This is the output we get. Yeah, exactly. Exactly. Thanks, Tima. Thanks, Joseph. Thanks, Omar. So in this case, right, we're searching through this list for anyone whose name matches this value. So in this case, we have an individual named Clayton Sharp, right? We're searching for everyone who just maybe they come to the event and they just say Clay. We want to be able to search through to find our guest, right? If we just typed C in here and reran this, you can see we'd get both Corinne and Clayton. So it's doing a general search on our list here. What is the big O notation? What is the time complexity of the search by name function? What do you all think? This one's a little tricky as well. Right, cool. Folks are guessing linear, right? Yeah, and why so? So we don't see any loops in here. We see a bunch of native methods. We don't see like a for loop or a while loop. So filter, remember filter, what it does is it iterates through each element of the array and it returns a new array for everything within each element that returns true at the position of the array, and sort of makes a new array from that. So this is going to filter through and only return the guess where this condition is true. Yeah, I think O of n is a good guess, but we have this dot includes method. This dot includes method, how does this work? What is this doing? So dot includes is going to search through a string and it's going to check for whether or not the substring is within that string, right? So if I had a string of Clayton, I'm searching for Clay, it's going to look through the entire string to see if Clay matches there. Same as if I looked at the end part of the string. So if I put TON in here, that'll still pull back Clayton. So this is actually a really tricky situation where includes is actually going to be iterating as well. The size here that matters is the size of the string. So for a name, because we haven't set any parameters here, if someone had a name that was 8 million characters long, it's probably not going to happen, 8 million characters long. But if that was true, then technically that would start to affect the size or the number of iterations that are happening within here. So even though we don't see that as part of the loop here, includes is going to be iterating through a data structure. In this case, though, it's going to be a string. So I think we would say that really, like technically, this is O(n) squared because the size of the array matters and the size of the string matters. I really like this example because this is where it gets like kind of crunchy. We have to talk about like, okay, realistically, what's happening here, right? I think you could make the case that, hey, it's people's names. There's going to be a limit there, right? And whatever that character limit is, even if it's 100 characters, 200 characters, that's a constant value. And so at a certain point, we can kind of ignore because people's names are not going to be insanely long. But if you didn't have the constraint, if this was instead like description, right? And it could be anywhere from 10 characters to Moby Dick sized, string of characters, it might be more representative, more truthful to say O(n) squared. So I think I might say O(n) squared, but I think you could absolutely make the case that this is really just because of how we live in the real world, an O(n) algorithm. Let me pause there. Any questions about that? Because it's a little tricky overall. Do folks understand why I said there could be a case for O(n) squared? Yeah, so I think you could say it's quadratic if there's no limit on the size of the name. Yeah, okay. All right. This is like, to me, again, it's interesting points. Like as engineers, we can get into the weeds of like, well, technically someone could have, they arrived from a different planet, could have a name that, goes on forever. But realistically, we're probably not dealing with that. So I think I would say both of these could be correct depending on the constraints you're realistically putting on your program. All right, we got a few minutes left. Let's take a look at get paid guest names. What does this function do? What is the purpose of this function? Yeah, it's going to return the guests who have paid. Love it, right? And it just returns the names as well. So good to know. Excellent. What is the big O notation of this function? What do you all think? Now I've stressed you out with that last one. It's like, oh, there could be tricks anywhere. What do you all think? What is the big O notation of get paid guest names? All right, Joseph Nazar saying O(n) squared. Cool. Any other thoughts? Okay, all right. Let's talk through it. So yes, get paid guest name is going to return the names of those guests. We have here two native array methods, right? So we have guests, so guest.filter. So first we're filtering through that list and returning a new array where it includes only those guests who have paid. Oh goodness, am I looking at the right thing here? Yeah. Okay. Um, then oh gosh, excuse me. Then we're just going to map over and return a new array that includes just the names of those individuals, right? Just the names of it. So we have a loop here and a loop here. These loops are right next to each other. Excuse me. Been yammering at you too much. My throat's mad at me about it. So we would say each of these, whoops. Right, these are each O of n. We're iterating over them once. However, we're not looking at a nested loop here, right? So let's think about it this way. For each iteration, for each element within guess, we're going to go over the entire guessed array once and then go over it again. So how we would represent that, I think the most accurate would just be to say this is O of 2n, not actually n squared, O of 2n. And so what I mean by that is if we have an array of just one element, right, that we're searching through, we're going to go over that array twice, right? Because we're going to loop over, filter through, and then potentially map over and get the names. If we had two items inside, we'd end up iterating over those elements 4 times. If we had 3 elements in here, we'd end up going over them 6 times. If we had 4 elements, if I can type it out, end up going over them 8 times. Shall agree? This makes sense, right? So the first time through, the worst case scenario here is that every single guest has paid, and that we're going to grab every single guest's name, right? So in this case, where there's 3 guests, we're saying, great, I have to iterate once, twice, 3 times. And then for each name, I'm iterating once, twice, 3 times. That's different than our O of n squared example. If you remember for that, was this where it was? I think this is where it was, or a place where it was. Remember here, we're getting 2 and then 4, 3, 9, 4, 16. Right? This is where we had O of n squared. Whereas in this situation, it just ends up increasing linearly, even though it is slightly larger. So remember that when we have these constant values, we end up just removing those. So I would categorize this as linear. I'd categorize this as linear. I know it's kind of tricky. So the thing to look for, here's maybe the clarification we can get at here. It's not just looking for the number of loops that are happening. It's also looking for where they're positioned with each other, right? So in our example from earlier with O of n squared, I'll go back over here for it. Right here, there's 2 different inputs that will affect the size of the overall, sorry, the time complexity of it. And all these values are getting compared against one another. It's not just that there's 2 for loops here, it's that they're nested within one another, and we're looping over all of those elements for each element in the other array. All right, let me pause there. Any questions about that? You're welcome to be mad about it. It's frustrating. It's okay. So typically if we have like 2 looping mechanisms next to each other, and it's iterating on the same loop, that actually might be O of n. Or again, we're just trying to look for what's the impact of the inputted array. All right, I'm gonna move on. These are all the little mistakes here are all the right ones to be making you all. This is all makes sense. All right, so for this one, for stringify guess status, what is the purpose of this function? What is the time complexity? What do you all think? What is the purpose of this function and what's the time complexity? Excellent. Thanks, Jess. I appreciate it. Thanks, Omar. Yes, this is going to put together a list of all of the guests and just print out, have they paid or have they not paid? Just puts together a little sentence here. What do y'all think time complexity wise? Time complexity wise, what do we think? I know a couple of these have been tricky for sure, but what do we think about this one? Stringify guess status. All right, Joseph says Oven. Any other thoughts? All right, yeah. Excellent. Oh, of two ends, just trying out some stuff. Love it. Yeah, so in this case, right, O of n, I would say is correct, right? So we have our guess array. Depending on the size of that array, we're going to loop over every single element within there. And then these lines in here, we do have a conditional statement here, but it's not actually, there's not an iteration happening, right? So in this case, we're just looping over and we're creating a new array, turning these values. So I would say that is linear. If there's more guess, there's going to be more iterations. If there's less guess, there would be less iterations. All right, we just have a few minutes left. Let's do this last one here. I'll just talk through this so we can get to the very end here. So what this one's going to do is it's going to mark a specific guest as paid. What happens here is we have an array of guests and we have a given ID. We're going to first search through and try and find the guest. And then if we did find a guest, we're going to go ahead and mark them equal to paid as true. And then we will go ahead and return that guest. So right here, we're changing Joanna Fernandez to be paid true. In this case, I would say this as well is going to be O of n because it is dependent based on the size of the array, right? So the size of the array determines the number of operations. This if statement does not do anything special. It's just a check at the very end. We're not iterating through, and it's conditional based on whether or not we've even found the guest. The worst case scenario here is that we're going to find the guest probably at the very end of the array and then go ahead and mark them as paid. All right, and that is our lab for today, y'all. So I know some of these were tricky. It can feel like a little confusing trying to figure out some of the key things that we discussed in terms of identifying the time complexity of different algorithms. Is first of all, look for the iterations in the loops. It means you have to keep an eye out for loops and while loops, while also keeping in mind things like dot filter, even things like index of or dot includes, and keeping in mind there that there's some iteration happening inside of there as well. The next thing you want to look for is whether those loops are nested inside of another loop. And that means there could be multiple iterations happening and leading to an O of n squared situation. We did not see in here any examples of O of log n, but we talked about that with binary search as a good example of that. see if there's anything else at the very end down here. Yeah, here's what I would just say as sort of a way to wrap up here. This is definitely a challenging topic for sure, and it can feel kind of uncertain. The only way to get better at this is to talk through it, continue practicing, and really getting into the habit of trying to identify your algorithms and what the time complexity is. I would say, like I said before, the most important thing as you all are beginning to code is to first just aim towards getting a correct answer for the problem you're trying to solve, a correct algorithm that does the thing you want it to do. And then after that, you can really worry about the efficiency of it and thinking about it. So I hope this was interesting. It's something we're going to talk about more with our upcoming algorithms on sorting. But if you're feeling now like you have to measure every single algorithm, no stress. Focus on getting your programs to work more than anything else. And hopefully this will help you think about some ways to perhaps identify some parts of your program that could use some improvements. I think we will stop there. We are at